Hello viewers, in this video we'll be looking at these questions. Determine which of the following function is one-to-one, and we're to justify our answer. In other words, we give reason for our conclusion. So here we have five functions from 1 to 5. Now let's begin with the first one. The first one is just a linear function. Now to show that a function is one-to-one, we have two methods. It's either we use the graphical method, or we can use the what we call the algebraic method. For the graphical method, you just need to graph this quickly. This is a linear graph. As you can see, the slope is positive, so it will be rising from left to right. And you can see that the y-intercept is nothing but -5, because this is the form of y is equals to what? Mx plus b. And now the x-intercept, to get the x-intercept, you just need to set y to 0, and that will give us 3x minus 5 equals to 0, and that will give us x is 5 over 3. And 5 over 3 is a little bit less than 2, so let's assume this is 2. So we're just going to have this line, something like this. So this is our line. And here, if you want to do the horizontal line test, definitely, if you take a horizontal line, say this one, let's say this is our horizontal line, is going to bisect our function only at one point. So you can see that what? This f is what? Or you can say by the horizontal line test, you see f is what? Is one-to-one. Okay. Now, for the algebraic method, all we need to do is we assume that the outputs are the same. So you assume that f of x1 is equals to f of x2. Then can we get x1 to be equals to x2? If x1 is equals to x2, it means that we have unique output, right? So here, what is f of x1? It's just going to be 3x1 minus 5. Just put x1 into the function is equals to, this will be 3x2 minus 5. And now 5 and 5 will go. So you have 3x1 is equals to what? 3x2, which simply means that x1 is equals to what? X2. So we started from assuming this, and we're able to get that x1 is equals to x2. So hence f is what? Is 1-to-1. All right, that's it. Number 2. Now for number 2, we have this function, which is a rational function. F of x is 3x minus 1 over x plus 2. Now here, still using two methods. Let's go. The graphical method here, it means we need to graph this function. Now, this is a rational function, and one thing we can see about this rational function is that we know that the vertical asymptote, it has a vertical asymptote at the 0 of the denominator, so which is x is equals to -2. And now we also know that it has a horizontal asymptote, because you see that the degree of the numerator and the degree of the denominator are the same. So the horizontal asymptote is just the coefficient, right? So it's just 3 over 1. The coefficient of x divided the leading term of the numerator divided by the leading coefficient, right? The ratio of the leading coefficient. So this is just 3. And we can see that we have an x-intercept. And what is the x-intercept? X-intercept for a rational function is usually the 0 of the what? The numerator. So you put 3x minus 1 equals to 0, and this will give us x is what? Is 1 over 3. Then what else do we need? We can have, do we have a y-intercept? A y-intercept is, let's say, when y is equals to 0, right? When x is equals to 0. If x is equals to 0, what do we have? So let's get y-intercept. y-intercept, just put x equals to 0. If you put x equals to 0, we're going to have at minus 1 over at minus 1 over 2. So that is our y-intercept. Now, quickly, I'll just do this. For details of this, you have to check the videos on sketching of rational functions, right? Now, here, let's do our vertical asymptote here. This is our vertical asymptote at x is equals to minus 2. And we're going to have a horizontal asymptote here at y is equals to what? Y is equals to 3. Then now we need to know where the function will be. So this graph, this is a vertical asymptote. So here we take test points, and we can take any point between minus infinity and minus 2. And if you try that, you will see that that number is going to be above, is going to be more than 3. So we're going to have something like this here, but we cannot cross. All we need to do, take a test point, take a number between minus infinity and minus 2, put it into the function. For example, if you take, let's just do it quickly. You take minus 3. If you put minus 3 here, here you give us minus 9, minus 1, right? And here we will have just minus 3. So this will give us what? Minus 1. So you can see here you have minus 10 over minus 1. So this is going to be 10. So you have a number. So it means you have a number 10. You can see 10 is bigger than 3. You can see this line is 3. So if you are between minus infinity and minus 2, your graph is going to be in this region. So it's going to go this way. And because this is a vertical asymptote, then we have this one. Also here, you can try your test point, but this graph, don't forget, this graph, we have x-intercept at where? 1 over 3. So this is going to be 1 over 3 somewhere here. And don't forget, this is also a horizontal asymptote. The graph is going to come this way and is going to cut the y-axis. Is going to cut the y-intercept. Our y-intercept is what? Is minus half. So we're going to have minus half somewhere here. Now, this is just a quick. Now, to know whether your graph will be in this region or in this region, all do you do? Take a test point. Take a number between, don't forget this is 0. Take a number between 0 and this, and try it in this function. For example, if you take 2, if you put 2 here, what do we have? If you put 2 in this function, you will have 6 minus 1, which is 5. And here you put 2 here, it's going to be what? 7. So you see this is a number. 5 over 7 is less than what? 3. And that is less than the horizontal asymptote. That is why we are in this region. Now, this is not the video for graph of rational function. So if you want full, you can check other videos. Now, here you see that this function is what? Is 1-to-1, because if we draw a horizontal line test, draw just horizontal line in any of the region, is going to cut the graph only at where? At just 1 point. So you can say by what? Horizontal test. When I say HT, I mean horizontal line test. F is what? Is 1-to-1. Okay, now quickly to the algebraic. What do you do? Just say, assume that f of x1 is equals to what? F of x2. So you can see sometimes it's easier to do the algebraic than the graphical method. Now f of x1 will just be 3x1 minus 1 over what? X1 plus 2 is equals to f of x2 will be 3x2 minus 1 over x2 plus 2. So we can cross multiply so that you have 3x minus 1 multiplied by x2 plus 2. It's equals to 3x minus 1 multiplied by x1 plus 2. right? Now, if you expand this, what do we get? This and this will give us 3x1, x2. This and this will give us plus what? 6x1. And what else? This and this will give us minus x2, then minus 2. So on this side, we'll have similar stuff, 3x2, x1. This and this will give us plus 6x2. Then we have minus x1. Then we have minus 2. Now we can cancel this term, and this one will go. And if you look carefully, you see that what else will go? Minus 2 will also go with what? With minus 2. Now, what do we have left? Here we have 6x1 minus what? x2. And this is equals to what? 6x2 minus what? Minus x1. So we can connect like terms. So this is going to be 6x1 plus x1. And this is going to be 6x2 plus what? x2. So here we have 7x1 is equals to 7x2. And surely x1 is equals to what? x2. So here we can also conclude that f is what? Is 1, 2, 1. For question number 3, it's f of x equals to x squared over 1 plus x squared. Please, this is x squared, not x cubed. Huh? So here, simply also here, we will just go directly to use the algebraic method. So you can try to see the graphical method as well. And now, with the algebraic method, we can say that what? F of x1 is equals to what? F of x2. We assume this. And now, what can we do? What we can do is to say that, okay, what is f of x1? This will just be x1 squared, right? Over 1 plus x2, x1 squared. Then here will be, everything will be for x2 then. And here we have 1 plus x2 squared. And so here, what we have now is going to be, we can cross multiply so that you have x1 squared, then 1 plus x squared. And this will be x2 squared, then 1 plus x1 squared, right? Then what we can do is just to expand. And if you expand here, you have x1 squared plus x1 squared, x2 squared. It's equals, so this will be x2 squared plus, this will be x2 squared, then x1 squared. Now, if you look at these two terms, they are the same. There's no difference. You see? This is x2 squared, this is x2 squared, this is x1 squared, this is x1 squared. Multiplication is commutative. So these two terms will go. So here we are left with what? We are left with just x1 squared equals to what? x2 squared. Now, can we always get x1 to be equals to x2? Now, let's see what happened here. We can transform this to this side, or we take square root of both sides, but let's do it this way. We take this to the other side, so we have equals to 0. And we can use difference of 2 square here. So this is x1 plus what? x2 equals to 0. And now, what does this mean? This means that x1 minus x2 is equals to 0, or x1 plus x2 is equals to 0. So from here we have x1 is equals to x2, but we have another solution here, which is saying that x1 is minus x2. Now, this is what we have. But you know, our goal is to get just x1 to be equals to x2. But in this case, we have additional results because x1 could be the same thing as minus x2. So this will fail. So it means, hence, f is not what? Is not 1 to 1. Okay, simply because we have this additional result here. Now, for the graphical method, you can try it. It's not that easy to sketch this graph. The graph of this function, it's just something like this way. So definitely it's not going to be a one-to-one function. You can try sketching this. Okay, now let's go quickly to the next question, which is question number 4. Question number 4 is what? It's f of x in this case is what? Is x squared minus 2x. And there is a condition that x should be greater equals to 1. So let's see what happened here. Now, for this one, I think we can use both. Now, graphical, how do we graph this? This we can graph our f of x. We can rewrite this is just a parabola. We can do completing the square. Half of the, or we found the vertex, but we can use completing the square. Half of the coefficient of x is minus 2. The coefficient of x is minus 2. The half is minus 1. So you square it, you add it, and you also remove it. But don't forget, we still have a condition. X is this. So this is nothing but x minus 1 square minus 1, and x is greater or equals to 1. So this is our f of x. And this we can easily graph. This is nothing but the graph of what? X squared shifted 1 unit to the right. So we are here at 1. Yes. And now you shift it down 1 unit down. So we are here. So this is minus 1. So this will be just something, an open up parabola, something like this, but not perfect, but it's okay to give us an idea of what we want. But here, what do we have? We have a condition that x has to be greater or equals to what? 1. So if this is 1, it means you are considering only the parts where the domain is greater than 1. So it means we don't have any business with the left-hand side. So we will have only this side. Yes. So you can see we have removed the left-hand side. The left-hand side, we remove it. Yes. So this is the graph of this function. And clearly, this is one-to-one. If you draw your horizontal lines wherever you want, it will only cross the graph at only one point. So you can say by the horizontal line test, should we use HT or just this one? You can say F is what? Is one-to-one. Now, for the geometric, this is graph, and this is algebraic or algebraic. What do? You said f of x1 is equals to what? F of x2. So this means that what? X1 square minus 2x1 is the same thing as x2 squared minus what? 2x2. So here, what can we do to show whether f of x1 is equals to f of x2? What can we do here? Now, if you look at this part, you can see that here we still have what? We have 2x1 and here we have 2x2. So we can do like completing the square for both sides. So this is going to be x1 square minus 2x1, right? If you do completing the square for this, it's going to be plus 1 minus 1. Then on this side also, you do completing the square. So you have this is going to be plus 1 minus 1. Now, if you look at this term here, what do we have here? This is nothing but x1 minus 1 square, then minus 1. And this side also is going to be x2, right? Still minus 1 square, then minus 1. So you see that we can drop both minus 1 and we just go with what? X1 minus this square, it's equals to x2 minus 1 square. Is that okay? Here, what we can do now is to what? To take the square root of both sides. So we have square root of x1 minus 1 square is equals to square root of x2 minus 1 all square. and this will give us absolute value of x minus 1, and this is what? Absolute value of x minus 1. Now, don't forget we have a condition that our what? The condition is that what? X is greater than equals to 1. So it means that even x1 must also be greater than 1, x2 also must also be greater equals to 1. So since x1 is greater than equals to 1, it means the term here is positive. The term here is also what? Is also positive. So in both cases, we can drop the absolute value and just write x minus 1 is equals to x2 minus 1. And this simply means that x1 is equals to x2. So also f is what? Is 1, 2, 1. Then lastly, question number 5. Question number 5 deals with absolute value function. I think f of x is equals to x minus 2 plus what? Plus a 3. But here we have a condition that x is greater than 0, equals to 0. Now let's see what happened here. We can try to graph this. Let's see the graphical method. If you try to graph this, this is nothing but the graph of absolute value of x shifted 2 units to the left. So we are here. 2 units to the right. Then you move it 3 units upward. So this is 3. So this is just something like this here, right? Like this. Okay, but look at the condition we have now. The condition we have is x is greater than what? 0. So if x is great, this is an absolute value graph. Is supposed to be going up to where? Infinity, minus infinity, and infinity. But since the condition is x greater equals to 0, so it means this is 0. So we can only take this part here. So we have to remove this part, all of this part. So it means we can only approach here. We can stop here because greater equals to 0. So this is the graph. But this side is longer now. This side will continue, right? Now this is the graph. And if you look at this graph, clearly it is not one-to-one. So the lesson here is that you have to be careful also of the what? The condition. The fact that you have a condition does not mean the function must be one-to-one. You have to check. Okay? So because here, you see now, if you draw a horizontal line, it's going to cross this one. It's going to cross more than once. So by horizontal line test, f is not what? 1 to 1. F is not 1 to 1. Then let's see the algebraic. For the algebraic, just assume f of x1 is equals to what? F of x2. So in this case, it means x1 is greater than 0 and x2 also has to be greater than 0. So here we will have absolute value of x1 minus 2 plus 3 is equals to absolute value of x2 minus 2 plus 3. We can drop the 3's so that you have absolute value of x1 minus 2 is equals to absolute value of x2 minus 2, right? Now, you see the problem here is that what? We know x1 is greater than 0. If x1 is greater than 0, if x1 is greater than 0 here, it means this, what we have here, sometimes it can be positive, sometimes it can be negative. For example, if I take x1 to be 5, because 5 is greater than 0, the content here will be what? Will be positive, because 5 minus 2 will be 3. But if I take x1 to be 1, 1 is also greater than 0. But in that case, 1 minus 2 is going to be negative. So you see, sometimes it could be positive, sometimes it could be negative. Same apply to this one. Sometimes it will be positive, sometimes it will be negative. So in this case, the condition given is not enough for me to remove the absolute value. And if you cannot remove the absolute value, we cannot conclude whether x1 is equals to x2. So it means that f, we just conclude f is not what? F is not one-to-one function. So either one-to-one. Okay, so I hope everything in this video is clear. If you have any question, just put it in the comment section. Thank you for watching.